Welcome to this CE 108 video. So in this video, what we're going to review is how to apply the Mohr circle to solve problem where you have to find in which direction the stress is maximum, or to see in which direction the given member is the most likely to break. So in this case, we are going to review an example where you have to construct a Mohr circle. As a reminder, the Mohr circle will give you in plane stress condition all the possible values that the normal stress and that the shear stress can take as a function of the direction. So to construct the Mohr circle, you need first to determine what's the value of the state of the stress. So you need to get the stress in a given set of axes x and y. You need to get the normal stress along x, the normal stress along y, and the shear stress in this plane. And based on this, based on the Mohr circle, you will be able to get all the possible values of the normal and the shear stress as a function of the direction. And based on this, you can quickly determine what is the maximum and the minimum value for the normal stress. So you can get the principal stress component, and you can get the maximum and the minimum value for the shear stress. So the maximum in plane shear stress or the minimum in plane shear stress. And in addition, you can quickly get the angle, so the direction according to which you will find those maximum value of normal stress and shear stress. As a reminder, brittle material typically break under tension. So if you want to see in which direction a brittle material is likely to break, then you would have to find the direction where the normal stress is maximum, where you have a tensile stress that is maximum. And in contrast, ductile material typically break due to shear. So in this case, if you consider a ductile material and want to see in which direction it's the most likely to break, then you would have to find the direction of the direction along which the shear stress is maximum or minimum. In this case, you can break with the same probability a given material by applying a positive or a negative shear stress. So in this case, only the absolute value of the shear stress matters, not the sign, which is different from the normal stress, since for the normal stress, a positive normal stress by convention is a tensile stress, while a negative normal stress is a compressive stress. And usually it's much easier to break material under tension than under compression. So in this case, the sign matters. And you only want, in this case, to find the direction along which the normal stress is maximum, where you have the maximum tension. But in this case, it's usually not useful to find the direction along which the normal stress is minimum. That would be the direction where you have the maximum compression, the most negative normal stress. But usually the material will always break due to tension, not due to compression. Okay, so let's see an application of the Mohr circle. Let's see an example of problem. So what we are going to consider is some kind of inverted pyramid like this. So you have a beam like this with a triangular shape, and so this beam is along the y-axis. So you have one y-axis going up like this. We're going to write y equals 0, the bottom of this inverted pyramid, and y equal L will be the upper limit of this member. And so this member is has a given width. So this would be the width of this member, and this member is going to be attached to a fixed support at the top, like this. Okay, so we are going to introduce a few dimensions. So first, the width of this inverted pyramid is going to be L, so the same L as the height of the member. Then we are going to introduce the width of the member. So we are going to say that here this distance we can call it R. It depends on y, and it's just going to be equal to y, so that when you reach the top of this member, so when y equal L, then the total width would be, in this case, 2L, 2 times R, where R equal y. So at y equal L, then the top becomes 2L. Okay, and we are going to consider that this beam is made of a material that is ductile. So we're going to consider that it's, for example, made of iron or made of another types of ductile material, which means that it's going to break due to a shear stress, not due to tension. And we're going to consider that this material has a given density rho, so the mass per unit of volume. And we're going to consider that in this case, this material is subjected to gravity. So you have, in this case, gravity is not neglected. The weight of the material is not neglected. So in this case, we account for the weight of the materials. Okay, and the question in this case, the goal of this problem is to find, assuming that the material has a given ultimate shear stress, so the ultimate shear stress would be the shear stress at which the material breaks. The goal of the problem is to find what is the maximum value of L, so the length of this member, what is the maximum length of this member before it breaks. So if this member is very small, then its weight is going to be very small, so the stress is going to be very small, so this material is not going to break. But if this material, if this member becomes larger, so if L, capital L becomes larger, then its weight is going to increase, so the stress is going to increase, and at some point the stress, the shear stress, is going to exceed the ultimate shear stress, so the material in this case would be likely to break. So we want to find what's the maximum value of the length L before the member breaks. Okay, so for this it's a Mohr circle problem, because in this case the weight is going to result in only a tensile load. So you will have a tension load being applied on the material. So we need to see how this tension is going to be converted into a shear stress that will cause eventually the failure of the material. So for this, we will need to be able to transform a normal stress in the y direction to see how it can be converted into a shear stress along another direction, and we have then to see for which value of L the shear stress is going to be large enough that it exceeds the ultimate shear stress. So for this, we will need to first determine what's the state of stress for this problem. So for this, it's an axial load problem, so we need to calculate the internal load, and based on this, get the internal stress. And in this case, we don't know directly where the member is going to break, like at which position Y is it likely to break. So first, we will need to calculate the internal load as a function of Y. Then based on this, calculate the stress, the normal stress as a function of Y. So for any Y between 0 and L, for any point within this member, we will need to calculate the normal stress. Based on this, we will draw a Mohr circle in order to convert this normal stress into a shear stress. And based on this, we will see what's the condition to have a fracture, or what's the maximum length before fracture is likely to happen. So for this, the beginning is just a conventional axial load problem. So we just need to calculate the internal load by using the method of section. So in this case, the step one is to identify the unknown. So in this case, you have a fixed support on the top that is going to apply a resistant force that is going up, that we can write N naught. And the first thing will be to find the value of this resistance N naught. And for this, we have to write the condition of equilibrium for this beam. So here, so far, we are missing one force, which is the weight of this material. So the weight is going to be applied at the center of gravity, and the weight is going to be going downwards. So the first thing is we need to calculate the value of the weight, and for this we need to calculate the mass of the material. The weight is going to be equal to the mass times the gravitational constant g. But for this, to get the mass, we need to get the volume. If we have the volume, then we can multiply it by the density. So we need to get the volume of this materials. So in this case, to get the weight, so we are going to first calculate the volume. So in this case, this triangle here can be decomposed into two rectangle triangle like this. So here we have the height of the member, which is L. Here on the top, this distance is also L. So then we can write that the volume of this material is going to be first equal to the area of this triangle. So this triangle is half of L by L square. So its area is L square divided by 2. Then we have 2 of those triangles, so we can multiply by 2. And then we need to multiply by the width. In this case, the width is L. So in this case, we find that the volume is L cube. So based on this, we can get the intensity of the weight. The intensity of the weight is the mass times G. The mass is the density times the volume times G. So in this case, we find that the weight is L cube times the density times G. So based on this, we can now write the condition of equilibrium for this entire member. So in this case, we are going to write that the sum of the projection of the forces along the y-axis is equal to 0. So in this case, first we have the force N naught, the resistance force N naught that is going towards the positive y, so it has a positive projection. And then we have the weight, it's going downwards towards the negative y, so it has a negative projection. Its projection is L3 rho g. The sum of those two forces has to be equal to 0 so that the member is balanced. So in this case, we find the value of the unknown, that the unknown is equal to L cube rho g, which is the value of the total weight of this member. Then based on this, now the next step is going to use the method of section to find the value of the internal load. So let me do that. Let's create a little bit of space. Okay, so now we need to use the method of section. So what we are going to do is to cut this member in two parts. We need to separate it into the bottom parts and the top part. So we need to choose one section. So we are going to choose for a given y. We are going to cut this material into parts, and we are going to only, in this case, isolate the bottom part. So if we do this, so it means that now the member that we are isolating is only the bottom part. So we are isolating the bottom part of this inverted pyramid. So the part that we are isolating goes from y equals 0 to a specific y that we are choosing, at which we are cutting the material into parts. And what we will want is to find the value of the load applied by the top part on the bottom part, which by definition is the internal load. In this case, the internal load depends on the y at which we are cutting the member in two parts. So in this case, the load always needs to be defined positively as pointing towards the outside. So the load is always positive if it's pointing towards the outside, if it's putting the member under tension. This is the same convention that we are using in this class. And then, so we need to write that this portion of the member is at equilibrium. If the member is at equilibrium, then every portion of this member also has to be at equilibrium. Here in this case, we are missing one force, which is the force that is applied on the bottom section, which is the weight of the bottom section. Remember that now, since we are isolating not the entire member, but just the bottom part of the member, we need to draw a free body diagram just for the bottom part of this member. That is to say, we only need to put the forces that are applied specifically on the member, not the forces that are applied to the rest of the member, only the forces that are applied to the bottom part that we are isolating. So in this case, the other forces that we are missing is the weight of this bottom part, which is going to be different from the weight of the entire member. So now we are going to write a new weight, which will be depending on y, depending on the portion of the bottom member that we are isolating, which will be the weight only of the bottom part that we are isolating. And that's the only two forces that are applied to this bottom part, the weight and the internal load, which is the load applied by the top part to the bottom part. Again, so we need to calculate first what's the value of the weight, and then to write that the internal load has to compensate the weight because this member has to be at equilibrium. So in this case, to get the weight, so we need again the volume. So the mass of this member is going to be given by the density times the volume. In this case, the volume, so same thing, it can be described as two rectangle triangle. In this case, so the height of this rectangle is y. At the bottom, so the width of this triangle is r as a function of y, which is also y. So same thing, this rectangle triangle is the half of a square of edge y, so its area is y square over 2. This is the area of this rectangle triangle. Then we have two of those triangle here, so we can multiply by 2, and then we need to multiply by the width, the thickness of this member, which is still L. So in this case, we find that the weight of this bottom part of the member is only, so I forgot to multiply by g, so we have rho g times y square times L, which is the weight of this bottom part of the cross section, which depends on y. So if y is equal to 0, then the bottom section has a 0 volume, so its weight would be 0. And if you are calculating, if you isolate, if you choose y equal L, so if it means that in this case you isolate the entire beam, the entire member, and in this case if you choose for y equal L, then you would find exactly the same value as the total weight that we derived earlier for the entire member. So then we can write the condition of equilibrium for this bottom part of the beam. So we have the internal load. In this case, the internal load is pointing towards the positive x, so it has a positive projection. We need to add the weight. The weight in this case is pointing downwards, so it's towards the negative y. It has a negative projection. And the sum of those two forces, of those two projections, has to be equal to 0. So we find that in this case, the internal load, which is as a function of y here, not as a function of x, is equal to rho g y square L. So this gives us the value of the internal load. Based on this, we can calculate now the value of the stress. So based on this, we can get the stress. So by definition, the stress as a function of y is going to be equal to the load divided by the area over which it is applied. That's the force divided by the area. That's the stress in the case of an actual load problem. So in this case, this stress is equal to the load. So the load is rho g y square times L, and the area over which it is applied. So the area is this area here. So let me draw it. So this is this area. This is the area over which the load is applied. So the value of this area is a rectangle. Its value is first the width of this rectangle. This width is 2y, and we need to multiply by the thickness, which is L. So this is the value of the surface at which the surface through which we are cutting the member into parts. This is the surface over which the load is applied. So to get the stress, we just need to take the load and divide it by the area over which it is applied. So based on this, now we have everything we need to calculate the state of stress, which is the first step to draw the Mohr circle. So now we have the state of stress. So in this case, so we said that the axis y is going up. Then we have an axis x that would be, for example, going towards the right, like this. In this case, so to get the state of stress, we need to find the value of the stress along x, the value of the stress along y, and the shear stress. So in this case, so what do we find? So in this case, the normal stress on X is equal to 0 because there is no stress that is applied on the X-axis. Here we only have a force, the weight that is applied along the Y-axis. So in this case, there is no forces along X. The beam is not going to be compressed or to be put under tension along the X-axis. So there is no normal stress along the X-axis in this case. Then the stress on Y, then we just calculated it. That's the stress that we just calculated. So in this case, the stress on Y is given by the density rho times G, the gravitational constant, times Y, the L disappears, and we just need to multiply by 2. So in this case, we just take this expression here that we just calculated, and we just simplify it by simplifying Y and simplifying by L as well. Okay, so we have the stress. We are just missing the shear stress, but in this case there is no shear stress. It's just an actual load problem, so there is no shear stress. Okay, so now we have the state of stress. So we said that this is a ductile material, so it's going to break due to shear stress. But in this case, there is no shear stress. It's only a pure tension along the y-axis. But it doesn't mean that there is not going to be a shear stress in another direction than this axis x and y. So in this case, we need to draw a Mohr circle to find is there a direction where you have a shear stress? If so, what is this direction where the shear stress is maximum? And based on this, we will see at which condition this shear stress will eventually becomes larger than the ultimate shear stress that the material can sustain before it breaks. Okay, so we are going to now draw the Mohr circle. So for this, the different steps. First, we are going to, so we just calculated the state of stress, which is always the first thing that you need to do for a Mohr circle. Then, so in this case, we are going to start to put the axis of the Mohr circle. So as a reminder, the axis x is giving you the stress along the x-axis. By convention, we draw the y-axis as going down, so that a clockwise rotation of the axis will also correspond to a clockwise rotation on the Mohr circle. As a reminder, in this case, the y-axis gives you the value of the shear stress. And so once you have this, the first thing is we need to find the position of the center of this Mohr circle. So the center is given at the average normal stress along the x-axis and at 0 along the y-axis. The center is always centered around 2 equals 0. So in this case, the average shear stress, that is to say, the average normal stress, sorry. So this is the average of sigma x and sigma y divided by 2. So in this case, sigma average is going to be rho gy divided by 4. Okay, so that gives us the position of the center. So the center, for example, is going to be here with a position 0 on the y-axis and a position rho gy divided by 4 on the x-axis. Then we need to place one point of this Mohr circle. So we know that the Mohr circle is going to give you all the possible values of the normal stress and the shear stress for all the possible directions. So we know that necessarily the original direction, the original set of axes x and y, the state of stress in this direction has to be one of the points of the Mohr circle. So here we need to place the state of stress, the point that corresponds to the state of stress in the original axis x and y. So we are going to put the point M that corresponds to the original state of stress. In this case, the position of this point M is given by just the value of this of its normal stress along x and the value of its shear stress in the original axis xy. In this case, sigma x is equal to 0. There is in this problem, whatever is the position of the point M, its normal stress is always going to be 0 on the x-axis. And same thing, there is no shear stress. Okay, so here we are not choosing a specific point M. This point M can be anywhere inside this member, but irrespectively of its position, this point M will have a 0 stress on X, will have a stress on Y that is given by the expression that we just found. So this expression will depend on the position Y. And this point M, at this point M, there will be no shear stress because there is no shear stress in this problem. So in this case, the point M is at 0, 0. So the point M would be here at 0, 0, at the origin of this set of axes. So based on this, now we have the center. We have the one point of this circle, so we can calculate, we know everything about this circle, so we can calculate its radius. So the radius of this circle is the distance between C and M. So in this case, the radius is going to be equal to rho g times y divided by 2. So the distance between the point C and the point M. And based on this, so we have the center of this circle, we have its radius. So now we have everything we need to draw this Mohr circle that gives us all the possible values of the normal stress and the shear stress according to the direction. So based on this, now we need to go back to the goal of this problem. The goal of this problem is to find for which length L the material is going to break. So the material is going to break, since it's a ductile material, is going to break due to the shear stress. So it's going to break if there is one point within this member. If there is only one point, if there is at least one point with this member that is experiencing a shear stress that is higher than the ultimate shear stress, then this material is going to break. So what we need to see here, what we need to do in this case, is to look for all the point M that belong to this member. We need to look at what is the maximum shear stress, what is the direction where you find the maximum shear stress. So we will find the maximum shear stress for all the points M, and based on this we will find what is the point M for which the maximum shear stress is actually the maximum throughout the member, and then we will check what is the condition for which that this shear stress still remains lower than the ultimate shear stress that the material can sustain. So in this case, the Mohr circle quickly tells you what is the maximum value of the shear stress. In this case, you have two possible values. The possible value where the shear stress is maximum or in the shear stress is minimum. In this case, the sign doesn't matter. The value of the shear stress is always equal to the radius. So it's plus the radius or minus the radius of the circle. This is a result that is always true. So in this case, it means that for a given point M that is at arbitrary position Y along this member, then we can calculate its maximum shear stress, which is going to be at 45 degrees in this case, and this maximum shear stress is given by the radius. I made a mistake here. The radius, there is a factor 4, so the radius of this circle in this case is rho times g times y divided by 4. So that gives you the value of the shear stress, the maximum shear stress at any point M belonging to this member, which is a stress that depends on y, depends on the position y. Okay, so then now we have the shear stress for every point y. Now we need to see what is the condition according to which there will be at least one point of this member that will break. So for this, what we can do is to enunciate the condition of integrity, so the condition at which the material will not break, at which the condition for which this member will not break. So the condition is that for all the point M, if this material is not going to break, it means that for all the point M of this member, then the maximum shear stress as a function of y needs to be always smaller than the ultimate shear stress. If there is at least one point M for which this condition is not true, if there is at least one point M for which the shear stress, the maximum in-plane shear stress becomes larger than the ultimate shear stress, then the material will break at this point. So the condition of integrity, that is to say, the condition at which the material will not break, is that for all the points M, whatever their altitude y, the maximum shear stress will not become larger than the ultimate shear stress. So in this case, it means that for this to be true, you need to have rho y times g divided by 4, so which is the value of the maximum shear stress. This needs to be always smaller than the ultimate shear stress. So this needs to be true for all the points M. This shear stress for all the points M, whatever the value of y, needs to be smaller than the ultimate shear stress. So in this case, the only thing we need to worry about in this case is that what is the point y at which this shear stress is the maximum. And in this case, if this maximum shear stress is lower than the ultimate shear stress, then we know that everywhere else throughout this member, since the shear stress will be even lower, then it has no chance to exceed the ultimate shear stress. So in this case, it means that this condition has to be true for every point y. So in this case, it means that for this condition to be true, it means that we need to look at what is the point y at which the shear stress is the maximum. And if at this point y at which the shear stress is the maximum, the shear stress is still lower than the ultimate shear stress, then it means that the shear stress everywhere throughout the member will never be higher than the ultimate shear stress. So here in this case, the shear stress is just proportional to y. So it's maximum for the maximum value that y can take. This maximum value is y equal L. So again, if we want this to be true, if we want that at any point throughout the beam, the shear stress does not exceed the ultimate shear stress, then the only thing that needs to be true is that the point at which the shear stress is the maximum, at this point, the shear stress needs to be smaller than the ultimate shear stress. So if it's true at y equal L, which is the point at which the shear stress is the maximum, then it's going to be true everywhere throughout the member. So in this case, the condition that needs to be satisfied is that at y equal L, that is to say, at this point, the shear stress is rho L times G divided by 4. This needs to be lower than the ultimate shear stress. So in this case, if we invert, we need to just remember what are we looking for here. What we are looking for is the maximum value of L. So in this case, we can invert this inequation to say that for the condition of integrity, for the condition for which this material is not going to break, then L has to be smaller than 4 times the ultimate shear stress divided by rho ng. So it means that for the material not to break, L has to be smaller than this critical value, which means that in this case, the maximum possible values for the length before the material will break is exactly this threshold value. So 4 times the ultimate shear stress divided by rho g. So in this case, it means that if the length of the material is the length of the member is smaller than this critical value, then the material will have a weight that is not intense enough to break the material, But if this material becomes larger than this length, then there will be enough stress that will be accumulating due to the large value of the weight, and in this case it's going to exceed the ultimate shear stress of this material, and this material is going to break at the very top at y equal L, which is the point at which the stress is maximum.